right. Hello, everyone, and welcome to another episode of Containers from the Couch. Today, we've got a special episode for you. If you'll recall, when we first started creating videos on Containers from the Couch, we created webinars for a workshop asset, EKSWorkshop.com. And today, we're unveiling a completely redesigned version of the workshop. And Justin and I are going to dive into the workshop today, go through some key design choices, things we've changed, things that are brand new. And Justin, it's your first time looking at this workshop, right? And hey, welcome.
Yeah, thanks. I'm very excited for this because, the workshop Containers from the Couch was built around EKS Workshop originally, where we were making video content specifically to show off the workshop, how it worked, get people hands-on with EKS and Kubernetes. Say, hey, this is how we get started. This is the path we think that you should take to learn this stuff. And shout out to Brent and Adam, who did pretty much all of those introduction videos 3 years ago now, and maintained the workshop for so long. And Sai's been working really hard with a whole group of people at AWS to help build the new version of the workshop that is better in many, many ways. And I'm excited to jump into it because I have tried really hard to not look at any of the content. I wanted to come at this with fresh eyes and say, like, hey, what does this actually look like for someone that's brand new to Kubernetes or brand new to this content, the workshop itself? So obviously I've been working with Kubernetes, but I don't know what's going on in the workshop. So I'm excited to dive into it with you. And we're going to do like a pair programming today where I'm the person running through the workshop, but Sai is hands-on keyboard actually running the commands. So I hope that we can go back and forth on explaining some of the stuff that's in there and then how it actually works when you apply it and run the commands.
Yep, absolutely. So that's kind of exactly what we're working with today. It's an all-new workshop. It is an evolution of a workshop we've had previously, but again, redesigned, completely built up from the ground up. And before we get into the workshop itself and some of the kind of key decisions we made in developing this workshop, I think for folks that are tuning in, maybe they're watching live or maybe they're watching, months after the fact, it's probably worth it, with the first workshop stream we're doing today, to talk a little bit about what is Kubernetes, what is Amazon EKS, why did we build an entire workshop experience around this product, this service on AWS. And Justin, I want to lean on you for this. I know it's kind of a heavy, loaded question here, but why and how does Kubernetes and Amazon EKS work?
Yeah, I mean, Kubernetes is very complex. It's something that, depending on who you're asking, how they use it, they're going to give different answers. It's the same thing like, what is a car? Right? Like a car is a complex thing that has a lot of different use cases. Some people use it for transportation. Some people use it to make money and to transport goods. And there's all reasons that you might use a car differently. To me, Kubernetes has fundamentally boiled down to a stateful REST API that is built for automation. The thing that you want to do with this API is automation, and it comes with some container workload primitives built in. It's extendable, it does some other things, but it eliminates some things that it's not, and some things it's not intended to be. And Kubernetes boils down to a way that we can automate infrastructure and workloads. Containerized workloads, absolutely. It's extended to some more things, but the focus of Kubernetes was really around how do we automate these containers. EKS, the Amazon hosted Kubernetes service, is really about managing Kubernetes easier. How do we take away a lot of the stuff that is hard in Kubernetes? Statefulness is really hard. There's a database behind it. That the database is distributed. It needs to have high availability. It needs to have backups. It needs to have all these things for automatic scaling. EKS does that for you. That is a big goal of EKS. Sai and I both are on the EKS team. We work really closely with the PMs and features and everything coming out for EKS. And we love making that better for customers because it takes away some of the challenges of running Kubernetes on your own. Fantastic API, very well designed, kind of hard to manage sometimes. And EKS is really designed to help take away some of that management from you, that burden of, hey, I need a database expert. I need someone that knows how to scale an API. I need someone that does all these things. Let's just let you use the API to deploy the workloads and make that side of it easier. So it comes with container primitives built in. because it's extensible and was made to be extended in various ways, it can be a lot of different things for people. But EKS running in Amazon helps you run containers inside of AWS using AWS primitives such as load balancers and EC2 for compute and EBS for storage. All these things come together to make an actual useful product for people just to run a workload.
Perfect. And I honestly couldn't explain it any better than that. Justin, you talked a little bit about what Kubernetes is not, and that kind of reminds me, I should probably explain a little bit about what this new EKS workshop we're unveiling isn't. I'll start off with saying that it's not meant to be a basic tutorial for what are containers in Kubernetes. Now, don't get me wrong, if you have a fundamental understanding of the technology, this workshop is the perfect place to start. And I think a term, Justin, you recently coined here, if you're an AWS expert, EKS expert, even if you are an expert, this workshop is going to be kind of a perfect place for you to look into some day two operations, complex networking scenarios, IP exhaustion problems, security groups, really complicated use cases, as well as we're going to start with kind of some fundamentals. But the key for all of this is that we really are focusing on Amazon EKS and its ecosystem of open source tooling and capabilities, all the integrations that you can set up with it, and not really diving into what is a container, what is the fundamental of Kubernetes. And for that, we have plenty of other resources on Amazon through our training and curriculum, and even the open source community has a lot of great content here. We didn't feel the need to reinvent the wheel. And so with that, I'd love to kind of share my screen here and unveil this new EKS workshop. Today, we do want to dive into it and start actually going through the first module. So you can see it here. We can see we've got a brand new UI. For folks that might be looking for the old one, you can still find it at archive.eksworkshop.com. But keep in mind that that older one is deprecated. Today, like we mentioned, it's Justin's basically first time looking at this content. And I really want to see how Justin experiences this workshop. And I want to see the kind of questions he has, because there's a lot of key choices that we made throughout this workshop. And I'm curious to get your thoughts on it, Justin. For example, we decide to use a tool called Customize to apply YAML. We decided to use the same sample app throughout the entire workshop. So, users get that consistency. They can expect to know that, the networking module where they set up their custom networking is working with the same app as the Fargate profile, which is used to deploy one portion of the application. By the way, that app is also open sourced and a great way to start learning about how to use containers on AWS. Whether it's EKS or App Runner or ECS, a lot of different functionalities there. But hey, Justin, what do you think? Let's go ahead and get started.
Yeah, let me post this in chat so people can see the example app coming out. I already posted a link for the announcement blog. I didn't post a link yet for the actual workshop. We should probably do that, huh?
Yeah. EKSworkshop.com. I figure that's the easy one.
That hopefully is the easiest one for anyone getting started.
So like I said, folks, it is live. You can actually access it right now. By the way, one of the really cool things that we did, and it's probably one of the first things we'll talk about here, Justin. So once I dive into the workshop here, I think people are firstly going to want to understand, how do I run this workshop?
Make your screen bigger. I can't read it from your side. I have it up over here, but I want to see it larger on your side too.
Oh, here we go. All right. Hopefully that's big enough.
Yeah.
Okay. So there's probably two ways you're ever going to run the EKS workshop. The first is at an AWS event. And if you do it this way, it's really streamlined for you. You don't need your own AWS account. We'll use the kind of pre-baked accounts. We'll load up the infrastructure for you. But for most people that are finding this digitally and want to go through it themselves, we have instructions to help you set this up in your own account. And so, Justin, I want you to kind of go through this first and tell me what you think about the decision we made here, because I know in the old workshop, this was a major pain point for customers wanting to set up their own workshop cluster environment.
Yeah, and I think some of that frustration just came with we're throwing a lot of new terms and tools at people right off the bat, where they say, I want to come learn Kubernetes. And we say, hold on a second, you got to learn this other stuff first. And sometimes that was difficult because we were doing tools that weren't familiar to them, where we said, here's a brand new tool like EKS control. Some people knew about it, some people didn't. We got a lot of feedback over the years that more and more people liked using Terraform. It was more familiar with them. The workflow was familiar. And so they knew Git, they knew Terraform. But beyond that, they were like, how do I do these other things? And this whole, the original workshop had a really good way to give people clean environments with Cloud9, give them an IDE and a shell that allowed them to just run with it. Because when we originally had the workshop, we had you run all the commands on your computer, and there was just a lot of variables that could not be accounted for because everyone has a different computer, different operating system, commands installed, all that stuff. So giving you a clean environment in Cloud9 was another way just to say, here's a shell that we know will work over and over again. Can you run this on your local machine? Probably, but we want to make sure that we have a great experience for people getting started. And so right off the bat, you should have an AWS account and you should be familiar with Git and have Terraform installed. And I think that's a great place to start because it lowers some of the barrier of new tools for some people. Hopefully you are familiar with at least a few of those things. If not, we try to hide some of the details where you don't need crazy complex shell commands. You don't need to know everything about Terraform. We're not going to ask you to modify the infrastructure or anything else. And Terraform, we're building on top of blueprints for Terraform, right, Si?
That's right. That's right. So the underlying automation, it's not custom baked. We're actually leveraging EKS blueprints for Terraform, which is a great project that allows you to basically just abstract away the complexity of all the different dependencies an artifact might have. For example, when deploying an EKS cluster, of course, you have to consider things like VPCs and subnets. I think that's the obvious piece. But what about when you're trying to set up additional open source tooling? Like you want to install Carpenter, an open source cluster autoscaler into the cluster, and maybe the load balancer controller and some other EKS add-ons and all the other things that you'll need to create a production-ready environment. Well, with the EKS blueprints for Terraform, it's honestly as easy as setting a flag to true. And you'll see that if you go to the open source repository for the EKS workshop, and actually it might just be worth me pulling it up right now. If we take a look at the workshop, we'll actually see, and let me make it bigger for you. We'll see a Terraform folder. And within this, basically, you come into here, you run that one command, Terraform apply, auto approve, and it'll kick off the Terraform here, and it'll actually start spinning up all of the dependencies. One I want to point out, if we go into the cluster module and we go to addons.tf, here's what I was talking about. That Boolean, this EKS cluster comes with Carpenter, the node termination handler for Spot. Load balancer controller, cluster autoscaler, kube cost, and all of these other add-ons. Justin, I know you've had this experience. If you had to install these manually outside of Terraform, whether it's ClickOps or whatever other automation tool you might be using, it really doesn't get this easy, right?
Each of those is multiple Terraform files for sure. You got variables, you have ways to integrate them together, you have all this stuff, and Blueprints gives you opinions on how some of that should be deployed based on what we're seeing from customers and how we engineered some of the tools to be used. And so with those, was that like 10 lines of true, you get a whole bunch of tools that are super valuable to have in any cluster. And so, yeah, this Terraform apply and you just get all that out of the box is awesome.
Yeah, and so here's the very first step, folks. Obviously, I'm not going to do this live for you. It does take some time to spin up all of the infrastructure. I wouldn't say not longer than an hour, but I've already spun up that environment. One key thing this Terraform does for you, not only does it deploy the cluster, but also spins up that IDE. And you mentioned this, Justin, is something we'd added to the previous workshop as well. It's a Cloud9 IDE, has all the tools pre-installed. So, you don't have to worry about the variables of having different versions or different types of binaries, different operating system. You have that kind of dedicated Cloud9 environment. But once you run that Terraform, by the way, folks, two things I want to caution. This is going to cost money. So you have to make sure you're managing your resources. And the TF state file is critical here for the cleanup process. But once you've got it there, we give you some instructions for how you want to clean it up, but then we point you to the next step, which is accessing the IDE. Okay, let's take a quick look at what that IDE looks like. Here's the Cloud9 environment. Very quickly, I'm going to run a few commands. That's way too small. I want to make that bigger. So let's run kubectl get pods and all namespaces. We can see we've got a number of my pods up and running already. The cluster environment actually comes pre-provisioned with, like we mentioned, all of the add-ons. So you're really ready to hit the ground running. And that's what I want to do with Justin here today. We'll go ahead and here, if we make this a little bigger, bring up the side nav bar again. I'd say, Justin, probably a good time for us to jump into the fundamentals module.
Sounds good.
All right, let's do it. Okay, so the way we've structured the workshop, we've got a number of these high-level use cases, and you can kind of see them along the top: fundamentals, auto-scaling, observability, so on. And for each lab within the module, you'll notice it's actually tagged with the word lab. One critical thing that we've done with this workshop, you can start at any lab at any point in the workshop. You could spin up an environment and immediately jump to a random lab in the networking or security section. The reason we've done it this way is because, let's be honest, to get through this entire workshop, it's going to take you the better part of an entire day. And so chances are folks don't have that much consecutive time to dedicate. So we want folks to be able to jump between different workshops and modules. Today we're going to start pretty consecutively from the beginning here. But Justin, I want you to, again, being your first time going through this content, or maybe your second time, let's start with the managed node groups one.
So, and it's a great point about the labs, because we found with the original workshop, it was kind of designed to have people go through top to bottom, everything in there to learn the entire set of what's going on. And they always built on top of each other. And this workshop does build on top of each other, but it's meant to be a little more bite-sized to say, like, hey, if you have the cluster running, you can just focus on load balancing. You can just focus on storage. You don't have to start from scratch every time. And so people come in and they want to learn different things at different times. So this workshop is really designed around that to say, hey, here's the piece we want you to learn in this module. Let's go ahead and just start here and get running with it.
Correct. And so I think to support that, you'll notice there's a command right at the start here. It says, before you start, prepare your environment for this section. And tells you to run a command, reset-environment. By the way, I just want to point out, anytime a command like this pops up, you can just highlight anywhere in this box, left click, and it'll copy it to your clipboard, and you can actually paste that directly into Cloud9 to execute the command.
Nice.
I'm not going to do this right now because the environment's already reset. It does take like a minute or two for that command to run, but let's go ahead, Justin. Let's start going through this first one.
Okay, so we're starting with compute, managed node groups. We want to start with something that every cluster needs, is some way to run those jobs. And can you go back to your terminal and list your nodes right now?
Yeah.
Nodes in Kubernetes are the computers where the workloads actually run. It's something that actually runs pods, runs workloads on top, or orchestrated with Kubernetes on top of a cloud provider or bare metal, wherever you're running this stuff. If you have EKS anywhere, not focused on this workshop, but you can have, different nodes running on your data center, whatever. Kubernetes can orchestrate that and say, here's where workloads are running. So we have 3 nodes here. I don't know how they got there. I don't really care how they got there. What we're going to focus on is how to provision something else with managed node groups. And managed node groups is part of EKS that allows you to get nodes without having to worry about it too much, without having to do manual work, to do upgrades, to connect them back to the cluster. It automatically is going to give those nodes some variables when they start up to say, here's your cluster, here's your VPC, here's your region, go connect to the API server and get ready to run workloads. You don't have to worry about it, because back in the day, when you're doing this manually, that's actually kind of a lot of steps. And I wrote bash scripts that would do this. People did different things to configure them. Ansible playbooks, all this stuff to say, okay, I need that node to talk to that cluster. Managed node groups take care of provisioning and also deprovisioning and upgrades. This is a huge benefit right there of managed node groups. We're just like, I just need some compute. How do I get that in my cluster? And so that's what we're focused on here in this managed node group section.
That's right. And so, this one, the very first module, we want to get folks kind of acquainted to how this environment works. One of the things you'll notice is that we use different CLI tools throughout the workshop. So for this particular command, we're using EKS CTL. And it asks us, look, let's inspect the default managed node group that was provisioned for you. And by the way, these nodes are as a result of two different managed node groups. So there's two in the first one and then one in the second one. And so let's run that node group command. And then in the default managed node group, we can see here, it's a little bit long here, but we've got two nodes, and we can see the instance type and a few other details about the auto-scaling group that was provisioned as part of that managed node group.
Now, and so that gives me compute that just is already attached to the cluster. And I saw you had a minimum of 2, right? Or desired of 2?
Yep. So min and desired is 2, and then the max size is set to 6.
And all that's saying, for anyone not familiar with node groups, this is an auto-scaling group inside of AWS. It's a managed auto-scaling group that gets some settings applied to it. Auto-scaling groups are a range of how many computers you want to be provisioned the same way. In this case, we say we want a minimum of 2, so never go below 2, and a maximum of 6, and we want 2 right now. You can change those sliders any way you want for your cluster. You could have 1 and 100. You could have whatever you want in those sliders. A lot of times that's meant for availability and budgeting. Where you say, hey, if I drop below 2 instances, I don't have any availability for my workloads, and my cluster might start failing. If I go over 6, I may be spending too much money or just be wasting compute because I don't actually have that much running. So in this case, this managed node group is kind of a manual slider where you're saying, this is how much I think I need for my requirements, whatever it is. Some people you can scale to 0, and you can say, hey, I don't need this to be scaled at all if there's nothing running. And I want to scale it up to 1,000 when I run jobs. And it depends on your workloads, how that gets applied. In this case, EKS control, we're just looking at the node group and saying, okay, this is what's in the node group. It's a managed node group. If we upgrade the version of EKS, we can also upgrade that managed node group, and it'll automatically deploy a new version to the cluster.
Got it. We got a pretty good question in the chat, actually. Do you have a cluster autoscaler built in with Blueprint? I'm guessing you mean with the Terraform EKS blueprints we're using. And yes, actually, we've got cluster autoscaler installed on this cluster. Justin, I have a feeling I know why he's asking this question. Since you're talking about autoscaling groups, why is cluster autoscaler important?
Yeah, with the managed node groups, we tell it our minimum and our maximum, but there's nothing that actually changes how many nodes are in the cluster, how many nodes are in that managed node group. The cluster autoscaler is responsible for doing that. When a workload comes in, when a pod comes in and says, hey, I can't be scheduled anywhere because there's not enough compute or it doesn't meet my requirements, the cluster autoscaler looks at that and says, hey, we need to add another node to this node group. And it just increases that desired count. It says, hey, we're going to go up 1 on desired from 2 to 3 in this case. So if we needed to scale up, that cluster autoscaler would automatically add a node to the cluster, and then we'd have 3 nodes in the cluster available. The workload can get scheduled, and everything's happy again. So cluster autoscaler scales up, but it also scales down. If our workloads scale down, it can look at the nodes and say, hey, this isn't being used as much as I expect it to be. I'm going to go ahead and remove a node so we can keep your costs a little closer to efficiency, to what you actually need to run in the workload in the cluster.
Yep. And so I think let me go ahead and clear this out. I think what we're going to do with the very first lab here is fairly straightforward. We want to show how you can add nodes to a managed node group. I'd say this is fairly straightforward. Now, for the most part in our workshop, we focus on the CLI commands, but at certain points, we do want to call out the UI experience. Now, if you're working with the cluster for the first time and you're going through that, that ClickOps experience of AWS, we do give you a link here where you can go and bump up the number of nodes using the UI. But I think for the most part, we want to make sure that you have the experience of doing the same thing on the CLI. And so here we see a couple of commands here to allow you to modify the scale of that node group. So very simply, let's run this first one. This is just going to get that node group again. We've done this before. And then now the second command here is going to scale that managed node group. And we can see here we're passing in nodes 3, minimum 3, and then maximum 6. So we're bumping up the minimum and the desired to 3, keeping the maximum at 6. Now, of course,
in this case, we're using the Psi autoscaler. This is you are the autoscaler, and this is how we used to do back in the day, right? Like if I had a workload and I needed to buy a new server or I need to add a VM to something, someone would manually go and say, okay, I created a new machine. Now we can deploy the application. Autoscaler will automatically do that for you. In this case, Psi ran that command manually, but it's the same APIs that the cluster autoscaler is going to hit.
Exactly. And so that was pretty quick. We got a message back saying the node group has been successfully scaled. Now, pretty common in this workshop, anytime you do something, we're going to make sure that we've confirmed that it happened. Now, this actually tends to take some time, but we can see that if we get the node group, we now see it updated to 363. That's min, max, and desired, up from 262. And then running the actual get nodes command against Kubernetes. So this again will take some time. I found that it doesn't happen immediately for that node to pop up. Whoops, didn't mean to run that scale command. It's not going to do anything, right? But what this is essentially, I just reran that command to scale up the node group. But given 2 to 3 minutes, we'll see that node get registered into the Kubernetes cluster, and then we'll see the node get started a few seconds after that.
And this all depends, a lot of this provisioning happens and depends on what's in your OS and how fast it can provision. If you're using one of the default images, it shouldn't take more than probably a few minutes. We've seen plenty of people, and I've done it to myself in the past, where I heavily customized my OS image to do a million things like yum updates. And if you're yum updating when you're provisioning an instance, that means you're pulling down all of the packages, you're figuring out what needs to be installed, you're updating it before the node is actually ready to be used inside the cluster. So make sure you keep that provisioning step as small as possible to make this provisioning happen as fast as possible.
That's right. We've got a question in chat. Is the minimum 1 or 0? Good question. You can actually scale managed node groups down to 0.
That is a newer feature for cluster autoscaler. So you do have the newer version of EKS and newer version of cluster autoscaler. I think 124 and above is where that landed. But yeah, you can, if you want to say, I'm just deleting all of my workloads, cluster autoscaler should scale you down to 0. And when you deploy new workloads, it'll scale up those managed node groups to have nodes.
That's right. And I ran the get nodes command with the -- watch, and we can see that a not ready node has come up. So let's actually just run that get nodes command again. By the way, we're just passing in a label selector to make sure we're just getting the ones in the default managed node group, the one that we edited. And we can see here that it's in a not ready state. Came up 37 seconds ago. We also give you a command. If you want to wait for it to come up, you can run this kubectl wait command. And then as soon as it comes up, actually that just came back. So boom, yeah, the worker node is up and ready. Okay, Justin, I think that about covers this particular piece of the Managed Node Group Labs.
Quick clarification for a question in chat. Kube control versus EKS control. EKS control is designed to manage the infrastructure for your EKS cluster. Kube control is designed to manage your workloads in the cluster. So EKS is managing the EKS service, node groups, that sort of stuff. Kube control is designed for managing workloads and things inside the cluster.
You got it. Next, I want to actually go into the pod affinity and anti-affinity module. I think this is a really interesting one that shows how you can leverage these affinity rules to define how pods are deployed across managed node groups. And this is particularly a pretty interesting example because sometimes you want workloads to be co-located to one another. And so I think this is a good way for us to go into the sample application that we've got here. Now, very quickly, I actually do want to bring up the GitHub repo for the sample app, which I think we shared a link for a little while.
It's somewhere back in the chat. I can get it again.
Yeah. But the reason I want to bring it up is I want to show folks that are watching the architecture of this application. You can see here we've got a microservices architected application. It's a retail store, and there's a number of components behind the scenes here. We use the same sample app across the entire workshop. What you can see here is that there's a number of different components here that power the actual retail sample store. Right now in the Affinity module, we're going to be playing with the checkout service. And the checkout service uses Redis behind the scenes. Now, critically, what we want is, for high availability, we want one instance of checkout across each of the nodes. And we want Redis to be deployed right next to the checkout pod. And so what we want is one pod per node, and then we want one Redis pod per node. And that way we have checkout and its Redis instance right next to it in the same node. That's going to reduce overall latency and improve our availability because we have multiple instances of checkout. I think it's a pretty cool use case, and that's kind of what we're doing with this very first lab here to demonstrate these affinity and anti-affinity rules.
And also good to point out that affinity, anti-affinity isn't just on a node level. That also includes per availability zone or per node group, anything that can be matched. So if I can say this label is designated to these types of nodes, I can say I don't ever want any other workloads to run on those. Or you can say I don't ever want to run on this type of machine, or I do want to run on this type of machine. So there's lots of things that you can apply to these rules. In this case, this is one way of showing that. And I like that you show customize in here. I think I might have jumped ahead. Let's go ahead and start where you were at.
Yep. So let's just jump through the instructions step by step here. So clear our terminal. Let's get the pods in the checkout namespace. By the way, if you do a get namespaces, you'll see that we've got a different namespace for each one of those components. So carts, catalog, checkout. Obviously, you see a lot of other things for the other components we've installed here, but we do have them chunked out fairly nicely. So we've only got one instance of the checkout and the checkout Redis pod. If we run this command, it'll actually show us using the pretty cool JSON path to kind of manipulate the output of kubectl that we've got the checkout and the Redis instance actually running on different nodes, and that's not ideal. Now, I very much likely could have had them both running on the same node. I got lucky today for our demo. They're running on different ones to kind of prove my point a little bit better. But I don't like the randomness, and we want to use affinity rules and anti-affinity rules to not make it so random. We want to set some structure for how these pieces are deployed. And so this comes to, I think, what you were about to bring up here, Justin, our first YAML configuration. And of course, everything in Kubernetes managed by declarative YAML, which is notoriously error-prone in workshop environments for folks that are updating things and might be updating it in the wrong place. And so we use customize to help streamline what these changes should look like. So here in the very first customize patch, maybe I made it a little bit too big. Look, this YAML is pretty big. I just want to know what exactly are we changing. So essentially, you go to the diff tab, and it'll tell you that what we're adding to the checkout deployment here is an affinity and anti-affinity rule. To break this down very quickly, I just want to show that basically we're giving the checkout pod an affinity, and we're setting this expression with the key value pair for Redis, and we're setting an anti-affinity for the key value pair service. And so essentially what this will do is say, don't deploy checkout anywhere else that the checkout service has been deployed. So anti-affinity for service. So if we go to the deployment checkout, we'll actually see that label right here. So we're saying an anti-affinity for itself. And essentially what that means is if that pod exists on that node, it'll deploy it. If it doesn't exist on that node, if it does exist, it won't deploy it. If it doesn't exist on that node, it will deploy it. So that's a fairly straightforward YAML change. We'll apply that. And
that -k command is customized for kubectl apply -k. That actually applies this overlay to override what the original information had. The thing I also think is really cool is with that affinity rule, you have required during scheduling. So if this cannot be fulfilled, let's say I do not have a node that doesn't have service running and does have Redis running, this pod will become unavailable. It will not schedule because the scheduler actually is looking at this rule and saying, oh, now what do I do? I can't provide both of these things that you want. That's where things like cluster autoscaler come in, because cluster autoscaler is going to look and say, hey, this node's not scheduled. So I'm going to create a new node and see if I can't land that job on this new node and meet that new requirement based on these demands. And it might need to reschedule jobs based to be able to meet this. And so that is something that happens. Cluster autoscaler would add a new node in this case if the pod says, hey, I can't be scheduled anywhere. The compute doesn't exist for me. So there are situations you can get into where you can say, hey, I made these rules, but nothing's happening. My job's not going. This workload needs to be deployed and it's not. You have to check to see if you have that capability of actually scheduling that job somewhere.
Absolutely. So like Justin mentioned, Customize is actually built into the kubectl CLI. It's an open source tool. I think it started separately, but it was actually eventually integrated into kubectl itself. So everyone has access to these kind of customized overlays. So we applied that YAML change. We'll see that all of the other things in checkout that are handled by that customized overlay were unchanged. So we just configured the checkout deployment. And in the next step, we're just going to scale that out 2 times. And then what we should see here is that well, actually, let's just go ahead and take a look. Because we want 2 pods, but we'll actually see that they're not deployed yet. So you'll see that the second checkout pod has not been deployed yet. And that's because it has an affinity rule to only deploy once Redis has been deployed on that node. This makes sense because traditionally you don't want the app to come up before its database. It makes more sense to start up the database, and then once it's up and running, you make sure the pod starts up alongside it. Okay, and so that checkout pod is currently going to be pending. Let's make it a little bit clearer here and just do the standard get pods. And there we go. We'll see that it's pending for 47 seconds. Okay, let's make sure I didn't forget any commands here. All right, now in the next YAML customization, I'm going to create an anti-affinity rule on the Redis pod, and that's going to match itself. So it's just saying don't deploy 2 instances of Redis on the same node. So we'll apply that. That should be fairly straightforward. It's not actually changing anything. We can do the rollout status. Okay, there we go. And then we'll scale the Redis out to 2 instances. Now, this is going to kick off kind of like a cascading effect. That second Redis pod will get started on a different node. And then the checkout pod, remember, which was pending, is going to say, hey, I can actually be scheduled now. The Redis pod came up. And so if we run the get pods, boom, we'll see that everything got started up. And I think that's exactly what I think that's probably the end of this particular lab. Yeah, so essentially what we've seen, if we run this command, is that now we're going to see one checkout instance running on one of the nodes, another one running on the second node, and a Redis instance for each one of those checkout pods alongside the instances. And in fact, since we have 3 nodes, because we bumped up the number of nodes in the previous lab to 3, we can actually scale it out 3 times. Of course,
you still have an anti-affinity for the service, right?
Yes. So the third one will be pending. So to fix that, we need to also scale up the checkout Redis deployment. And I'm going off the workshop script here.
That's all right. But I was curious because Is the service the workload we don't want to be running with? Is that on a different node group, or is it on one of those 3 nodes inside this managed node group?
So they're all going to be in the same managed node group. I think the anti-affinity you're talking about is we don't want to spin up a checkout pod if we don't have the analogous Redis pod also running in that same node. As soon as the Redis pod comes up, then we get the checkout pod as well. And that's what we see here. It was pending. And then as soon as we scaled up the Redis pod to 3 instances, it used that 3rd node, spun up another Redis instance, and then that let the checkout pod get scheduled.
Actually, a great question here in chat. Would it be better to run Redis as an init container for checkout, so that the container in the pod, we have 2 containers, and Redis runs with that pod if we wanted them co-located like that every time?
Yeah. That's another great approach for basically solving the same thing. In this particular lab, we wanted to demonstrate the anti-affinity and affinity rules, but that's a great point.
One of the downsides of init containers is if you have multiple of them, you can't order them. So if I have a sidecar and I have Redis, I can't order them necessarily, and it ties the life cycle of both of those containers together. Where if I need to deploy a new Redis container or a new checkout container, I have to deploy both. Whereas Redis is stateful, if depending on how I'm using it, right? Like I might have it as a cache and I want to keep the cache. So I could only deploy the checkout or only deploy Redis depending on what I actually want to deploy an update to. So there are pros and cons of doing it that way, that maybe doing it with an affinity rule might be a better solution, just because of that coupling of these things are always shipped together and I always want them in a clean state. Sure, that makes sense. Well, I was wrong. You can order init containers. You can't order sidecars. I'm sorry, I spoke wrong. Init containers do run in order. That's right. But a sidecar, if we have multiple long running pods with it, I can't order all of them together.
That's right. And yeah, Rafa in chat, it's the other issue. You can't start multiple in parallel, right? That's
init containers run one after another. That's right.
Right. Okay, so I think this kind of showcases, I really wanted an opportunity to talk about why we chose Kustomize. So I'm glad we went through this to kind of showcase exactly where Kustomize is useful, because you kind of have to admit, when you have to start making these large diffs in YAML, where you're nesting changes in multiple levels, YAML is notoriously pretty strict, which is a good thing when working with configuration, but a bad thing when you're in a workshop environment and you just want to update a YAML file. By the way, if you want to make that change manually, we don't stop you. You're free to navigate to that folder directory and change the YAML yourself manually and apply it. We just give this as a streamlined option.
And yeah, Kustomize is great at repeatable manipulation. If I need to do something over and over again, or I want to share this configuration, say, hey, this is the thing, this is the patch you need, I don't need to tell you go edit that file, because you might end up with spacing issues. We don't want you to troubleshoot editor problems right now. We want you to troubleshoot or learn the actual what's happening in the cluster. And that's why Kustomize is a great fit here, because it's just, here's the spec we need you to patch. Here's the deployment that already exists in a generic sense. And here's how we want you to override it one step at a time. And that's repeatable over and over again. And you don't have to worry about how to exit Vim. That's not a problem we're dealing with right now. It's just, here's your patch and here's that YAML.
Yep. All right, folks. So I think that's about as much time as I want to spend on managed node groups. We could also go into taints, spot instances, upgrading AMIs, but we'll leave that as an exercise for you. Next, I want to get into Fargate. But look, we got halfway through a module. We don't necessarily want to go through the steps to clean up all the things that we did. And so here's a perfect case for why we need something like the reset environment. Say I got bored of going through the managed node group module, I want to go somewhere else. I can simply take this command, run reset environment. In about a minute or two, it's going to reset my cluster environment to as if I just started the workshop. I think this was my favorite thing. One of my favorite things, at least, about the workshop is that you don't have to go through consecutively, and you can easily get this fresh environment to work with. But while that's running, Justin,
and reset environment's doing the cluster as well. It's saying resetting all of the workloads and managed node groups to how it was initially provisioned.
Exactly. Yeah. And so
That's
the
awesome.
node group goes back to the original size and it changes the configuration. By the way, this is another cool thing about using Customize. We made all these changes, but now to get back to the original configuration, we just have to apply the original Customize folder of YAML. All the changes we made would be erased. And you can imagine in production, this is a great paradigm to have access to is, whether you're deploying to dev, test, prod environments, whether you need to roll back or roll out a new version, to have that easy ability to reset config, I think is honestly really awesome. And we do expect people to use the EKS Workshop repo to help lay out their own, production grade workloads. Of course, the EKS Workshop out of the box is not production ready, but we do follow best practices, and we do expect folks to be able to use it as an example. That being said, actually, we can see it's asking the EKS node group to go back to the initial sizing. It's going to go through all those steps to reset our environment. But hey, now, Justin, we're on to the next piece here. You gave us great explanations for Kubernetes, EKS, managed node groups. I'm going to lean on you again here. What's Fargate?
Go down to that diagram, because that's a great diagram right there. And we can just start with that. And we already know that inside our cluster, we need to have some compute available to run the pods. There has to be somewhere that these things run. And we have managed node groups that are auto scaling to say, hey, I need 4 identical nodes that look this way. They're going to run pods. And I can match those based on affinity rules, all that sort of stuff. These are just standard VMs. These are VMs that run, and in Kubernetes, they run multiple workloads per VM, typically, where a VM is large enough to handle maybe 5 or 6 or 100 containers. And we could say, just run them all, and they'll all work together because I can have fewer VMs to manage with more workloads on them. It might be good in a optimal sense if you're running the same workload or same type of workload to be able to scale things that way. And people have been doing it for a long time, even before Kubernetes. So it's just a common way. Auto-scaling groups have existed for a long time to let people scale their workloads in this cookie cutter. One versus the other looks pretty much the same. Fargate is a serverless container image or VM, essentially, where it is a managed compute layer that allows you to still run workloads, but in a sense that you don't actually need to manage the OS. You don't need to manage these updates. What you get out of Fargate is a one-to-one matching of a pod on a VM, and that allows you to scale them horizontally. The same amount of pods you have will be the same amount of VMs if you're running them all in Fargate. And you don't worry about anything under the covers below your workload. That should all be managed for you. You just say like, hey, I just need this to run somewhere. Just create it for me. I don't really care. Just give me a computer and this will run. And that's where Fargate really shines, because when we look at serverless for functions in Lambda, you don't care about anything below your code. You can deploy a Lambda function and say, just make this run whenever I get a request. That is event-based architecture, where when a request comes in, I need to do something. Fargate's is a container-based serverless infrastructure where the container is continually running. It's not event-based like Lambda. The container is always running, so it's always ready to receive those requests. It's always just available inside the cluster. I can query it. I can get those logs. It is one instance of the container per Fargate node versus Lambda, where if I get 100 requests, I get 100 different Lambda functions. Both great options to running workloads, but in a containerized workload with Kubernetes, with EKS, Fargate is the solution you want. A lot of people think EKS and Fargate are different things. That is not the case. EKS can use Fargate or EC2 to run the workloads. And that's the biggest difference, where how much of it do you need to own? How much tuning do you need to do? How much configuration do you want? Depends on if you should be using Fargate or EC2.
And we got a question in the chat here. Does Fargate automatically scale without the need for defining auto scaling groups? And yes, absolutely. And I think that's kind of one of the big advantages of it for certain workloads, like Justin was saying, that you don't really care about the underlying details of exactly how the instance is set up, whether they're GPU enabled or whatever they might be, and the auto scaling group specifics. There are certain workloads where you just say, look, manage the scale of this for me, manage the deployment, manage the instances, and if traffic exceeds my limits and scale it up for me, and scale it back down automatically when I don't need it anymore. And of course, these are all things that you can configure when working with managed node groups. Fargate simply kind of streamlines some of those decisions you need to make, lowering your overall, cognitive overload when you're managing a Kubernetes cluster. And so there are some workloads, I'd say, that are really great for Fargate. And for example, I think one is when you're working with Carpenter, there's a controller mechanism here that enables it to actually manage the scale of your cluster. And so that controller mechanism looks at all of your other nodes and all your unscheduled pods and what your cluster layout looks like. So you never want that to go down. You never want that controller to disappear, whether you accidentally move a managed node group or you're doing some sort of AMI updates or whatever it might be. You want that controller to be always running. And so that's a great example of when you would want to use Fargate. In this particular... Sorry, go ahead.
The workshop, I know, I'm positive we'll get into how we're going to provision that. But there are some downsides to Fargate that I do want to point out right now, where things like daemon sets aren't supported because it's a one-to-one pod matching of every pod gets a Fargate node. And so you don't have to worry about auto-scaling groups. You don't have to worry about the cluster autoscaler because when you scale up your pod, you'll automatically get a Fargate node. But that means that if I need to run a daemon set on everything, the daemon set isn't going to be triggered for those Fargate nodes because those are only for running your workload pods. Fargate also doesn't have as much variety as EC2 does out of the box. Like EC2 has literally hundreds of instance types that you can pick and choose. Do you want Graviton ARM processors? Do you want GPUs? Do you want both? Do you want EBS optimization? All these things. Fargate simplifies a lot of that decision process, but also can limit some of the things that you can run in Fargate. So there are some great workloads that run in Fargate. It lowers that barrier or that cognitive load for you. But when you say, hey, I need to tune these things, I need to make these changes, or I need to own part of this infrastructure, that's when you should probably switch to EC2 and say, this is the thing that I know I need for my workload. Let's go ahead and make sure that we have those separate.
Yep. And so the workshop is going to go through the process of enabling Fargate and then doing some activities working with Fargate. I think it's worth going through this first one. I do want to point out, the way Fargate works, you create this Fargate profile and you create a selector within it. And that selector tells it which pods it should consider to be running on Fargate.
I'm going to sit down for Fargate because now I'm just getting too excited for this. I need to sit down.
Now, very recently, we actually created a new feature for Fargate. We released a new feature, rather. Now, we enable you to select namespaces with a wildcard. So before, every Fargate profile, you had to select a specific namespace. And with only 5 selectors for each profile, some customers ended up having to create way too many Fargate profiles because sometimes the namespace, some companies are using namespaces in a different way and creating them on the fly or dynamically. And so for that, we now have support for wildcards in the namespace selector. Actually, I noticed we don't have that documented in the workshop. That might be something I'll open an issue. We'll get that added to the workshop. That reminds me, by the way, folks that are watching right now that want to contribute to the workshop, we've established contributing guidelines. We're going to have a monthly community meeting. We really want to accept contributions from the community, from partners, from the open source ecosystem. Now, I will say we're going to restrict certain submissions. We want to fit with our open source guidelines and stick with partners that have an open source component in their solutions and tooling. But look, we're happy to accept PRs and evaluate PRs. So if you're interested in contributing modules to the workshop, it's a great place to get started.
Fargate profiles, when I was getting started, were confusing to me because I didn't know how they were implemented. Now that I understand, Fargate profiles are admission webhooks. There's webhook inside of Kubernetes. It's not an abstract thing. It's not something that's magic behind the scenes. It uses a webhook that looks at the job when you submit it, and it checks what you have defined on your Fargate profiles. So we have these matches that we say, hey, if it's in a namespace or if it has this label, whatever it is, we want to match that, and then we apply with that webhook, apply a node selector essentially that says you need to schedule on a Fargate node, and we're going to provision that for you. And so that makes sure that that makes sure that the scheduler doesn't automatically send it over to the existing nodes, because if I send a new workload in the cluster, the scheduler is just going to say, oh, I have availability, let's put it on this node. But with the Fargate profiles, we make sure that that doesn't go land on non-Fargate nodes. So it's a webhook inside the cluster. And it's something that, again, to me was really confusing, just because it was this magic thing that happened. I'm like, I don't know how you got this node and my workload ended up there and not somewhere else. But if we look at how Kubernetes works with webhooks and applying label selectors and taints, we can see how that logically progresses into, oh, I can make any workload that comes in with this namespace or this match of some sort, labels, whatever the case, go on a specific node. We just covered that. And you can do that with Fargate as well. Fargate just happens to be fully managed AWS infrastructure.
That's right. And so we can see that the profile that we've created here has a label selector. So any pods with the label Fargate : yes are going to get picked to run in Fargate. Now, so let's quickly check, why isn't the checkout service already running within Fargate, right? And we'll see that it doesn't have the label Fargate yes. And so we're going to use our favorite, customize, add that Fargate.yes. By the way, I love this so much. You can see the full diff
awesome.
checkout. But you can also just click this diff and see that, hey, look, we're just adding this one line. We'll apply it and check the rollout status. This should be fairly instant. We're just waiting for the deployment to restart with the label. So it's pending termination. I guess not instant.
Well, and what's happening right now, right? Because we applied the patch, and now in Kubernetes, it sees a new object. It actually gets a new object that goes through the workflow of seeing webhooks and all that stuff to be evaluated. Where should this go now? Because we've modified the object and we send it back to the API. And in this case, that webhook says, hey, we have a new label. That label matches, we want Fargate. So now we're going to provision those nodes. And so the Fargate nodes are actually coming up to be able to run the workloads based on that new label matching. And so it goes through the entire workflow of simply saying kube control apply. But in this case, we have a specific node selector that says we also need a Fargate node. So let's create that node in the process.
That's right. And I'm not sure why it's getting hung up on terminating. Let's run that one more time. Let's see what's going on here. Yep. Okay. Let's see. Get pods in checkout. This container is creating. Let's check out the events. No errors yet. I think it's just waiting for Fargate to spin up the
Check the nodes.
Sorry, what was that?
Check the nodes. Do we have a Fargate node?
We do. Oh, I don't have that alias.
We need to add that alias. That's a PR. If someone wants to add that PR to our IDE environment, there needs to be a K alias.
Yeah, it gets me every time. Okay, so the Fargate profile node, it does exist. Let's see. All right. It just took a little while, but we've successfully rolled it out. So if we run the get pods again, and let's actually describe this pod.
Did your checkout service have a pod disruption budget? That's why it probably would have taken a long time.
But I'm fairly certain we don't have one of those. So scrolling up here, I just want to see what node it's running on. Let's see. Okay, we do know it's been triggered by the Fargate scheduler. So I can assume it's, oh, here we go. Fargate IP, blah, blah, blah. And that's how we've basically confirmed that the checkout pod is running in Fargate now. Couple more things that we do in this particular workshop are related to kind of understanding the different labels of what defines a Fargate workload. Resource allocation, we go through how do we change how much, what the resource limits for these pods should be, and then how you actually scale the workload on Fargate. We've got about 30 minutes left here. Justin, it's probably worth us. Let's jump to the next part of the fundamentals module here. I do want to try and make it through at least all of the high level labs in here.
Yeah, we need to expose some of these services.
Let's do it. So right now we're not exposing the UI application, and so we can actually see that if if we do kubectl get pods in the UI namespace, and then let's describe the pod that's running. We'll see that actually it probably makes more sense to describe the service.
Yeah, look at the service, right?
So taking a look at the service, we can see that it's a type of cluster IP. Essentially what that means is it only has an IP address for internal access. So if you're within the Kubernetes network, then you can do a curl against this IP and access the UI. But of course, that's not good for our users. Our users need to be able to access the application. And believe it or not, there's quite a few ways to do this. And in this workshop, we go through what we believe is the best practices when working within an AWS environment. You're running in EC2 VPC and these subnets. What's the best way to expose our application to the public world? And that begins with the AWS Load Balancer Controller. Justin, I'll lean on you again here.
I was replying to some of our awesome questions in chat. So the load balancer control. So by default, Kubernetes has services. Services are the only thing that you actually expose in Kubernetes. You don't expose pods directly. You have to have a service, which is an abstraction around multiple pods. They get matched to a service, and then we have all these endpoints. So typical load balancer, we have one load balancer and a bunch of endpoints underneath it. We have different servers. We have different port numbers, we have different something behind the load balancer, and it balances per instance behind it. In the case of pods, we have multiple pods, and a load balancer just balances that load between all those endpoints. The AWS Load Balancer Controller gives you AWS load balancers, the managed load balancers in AWS that align to pods or services that do the same thing. Services in Kubernetes kind of act as a load balancer, but it's just a software load balancer in DNS. It's not actually like a physical thing that exposes anything. Cluster IP that Sai pointed out before, the service is going to get an IP just like that. And inside the cluster, they can talk to each other. From outside the cluster, I need something that exists that says, hey, I'm exposing this DNS endpoint, and I will balance load between all these pods behind the scene. So we need a service, and we need a load balancer to actually do that exposing of services.
Now, Kubernetes actually, it does a lot of this for us. And actually, when we set it up, it'll do everything for us. But the idea is we've got a lot of different nodes. And somewhere in all those nodes, our service is running. And our service has its own kind of port that it's listening on. The node has its own IP address. And then now what we're doing is setting up that other load balancer outside all of this to route to it. So Kubernetes really does help us out. This concept of a service is going to wrap all of the pods that service is responsible for, and say, kind of like a round robin load balancing. It's going to say any request that comes in from that ELB is going to hit our Kubernetes load balancer, which then gets distributed to one of the pods that are running to represent that workload. In this case, we only have one instance of the UI running. It's got a cluster IP, which is great, but I can't curl this, and it does not have an external IP. So that's what we want to fix right now. And so let's go ahead and get into it. I'm not going to run the reset environment. I don't think there's anything critical that we've changed in this namespace, so it shouldn't be a problem. Let's take a look. Now, what we're saying here is that we want to use the type load balancer to expose this application. I see a typo, actually. That's not the customize, though, so we should be OK. We want to use the type load balancer to expose this. We've already installed the load balancer add-on. And so let's take a look at our microservices. So this is the first command it's asking us to run to say, hey, let's just take a look at all of the services that we have and make sure that they're not externally accessible. And they're not. But they are listening on ports internally. And notably, we want to make sure the UI component is accessible. Scrolling down here, we already did this, but describing the UI service, we can see there's a cluster IP running on IPv4. Let's go ahead and create the load balancer. Now, first thing we'll need to do here is actually apply this, this NLB YAML, so this service. And so what this is going to essentially do is change that UI to be a load balancer instead of cluster IP. And so we'll run that customize and then run that exact same describe service UI again. Sorry, let's see. Here we go. Sorry, we just created the NLB. We haven't modified the UI service just yet. And so with this UI NLB, essentially, instead of just using that same service, we created a second one. And now we can see that we've got an external IP.
And the load balancer controller knows the difference between different types of load balancers. There's load balancers that'll just do network connections, the NLB, the network load balancer. There's load balancers that do application layer load balancing, which give you benefits such as like header injection and figuring out your HTTP endpoints. So the ALB for an application load balancer versus an NLB versus an ELB, the load balancer controller can know which one you actually want. And in this case, we're looking at an NLB. So the default expose a service in Kubernetes doesn't know about those things. It only does ELBs, and it doesn't do some of the more fine-grained controls you might want for those different types of load balancing. And so in this case, we wanted an NLB for network load balancing layer 4 without HTTP injection or header routing or endpoints and all that sort of stuff.
And what's cool about the flow in the workshop is that we'll actually point you towards that ELB that's got created. So by running this command, and you'll notice it's not kubectl, not EKS it's an AWS CLI command. We'll see that a load balancer actually got created for us using the ELB v2 CLI prefix. We'll see that is coming up right now. Here's ARN. You can go into AWS. You can go to the EC2 interface and actually see this load balancer being created, the different AZs that it's kind of registered to. And so I think this piece is pretty cool. This is something that we wanted to add into the workshop so that you know what's actually happening behind the scenes in the AWS infrastructure. Because a lot of times it's a little bit nebulous. You're working within the Kubernetes context to know what's happening behind the scenes. So what does this tell us? It tells us that this NLB is accessible over the public internet, and it's, again, using those public subnets that are in our VPC. A couple other things that we'll ask you to do here in workshop. First, we set a couple of environment variables for the ALB's ARN and the target group ARN, and then we're going to run the describe target health. Now, one of the things that kind of bugs me every time I did this was sitting there and constantly hitting refresh to make sure that UI is accessible, but it takes some time. And so by running this describe target health, we can see that it's still setting up that load balancer for us. It's doing initial health checks right now, a couple of things that it needs to do before it shows as healthy. And so if we go back and get that...
Why are there 3 endpoints there? I have one pod running. Why do I got all 3 endpoints?
Well, that's going to be for each of the subnets, so the target groups. And so hitting it now, boom, there we go. We can see the retail store application. In fact, if you want to hit this at home, you can hit it as well. I'm not going to paste this into chat now, but it is publicly accessible. And boom, we've exposed our service on AWS through the load balancer. By the way, the point of this exercise is to showcase how that load balancer add-on is basically translating the commands that are coming in through Kubernetes API to actual resources in AWS backend.
All of these things that the Kubernetes controllers are doing are APIs that you could run manually. You could set up this infrastructure all with Terraform or with the AWS CLI, and you could do the same commands. Kubernetes just knows how to connect those things together of, I have nodes that are exposing a port that have a pod running on them. I need to connect that to a load balancer as an endpoint. It's automatically registering that. This is just data that Kubernetes is saying, this is where it exists. Here's how I need to connect it. Here's the APIs I need to actually make this thing happen.
Yeah, and sorry, I think to answer your question earlier, I mentioned that these were the different subnets. These are actually pointing to the different nodes, I believe, in the node group, and we can kind of see that over here as well.
Yeah, when you go back and describe that service, you'll see that it's exposing a port 31898. And that's the port that gets exposed on every node in the cluster. That just gets reserved as a service. When you have a cluster IP, that port is going to be available. 31, yeah, there it is at the end there. Yeah, 31.898.
Yep.
And that gets exposed everywhere. And then every one of those nodes is a backend for the load balancer. But the UI is only running on one of them. So when the load balancer comes in, it doesn't really know necessarily where. It says all of them are healthy, but only one of them has a service running. The way that gets routed is the load balancer sends traffic to a node. If the node is running the pod, great, it's just going to serve the traffic. If that node's not running the pod, the kube proxy, which runs on the node, is going to send it to another node. It's going to send it to the actual node that's running the application to then return traffic. So you would get every node as available on the load balancer because it's a lot more expensive to attach and detach nodes as endpoints to a load balancer than it is to change IP rules on the node to say, oh, send traffic over here, and I'm just going to reroute you to where that's running. If you're running a daemon set that exposes the same port, then it's always going to land on a node that runs the application. But it's a small distinction that sometimes is confusing to me, where even if I have one pod running, I get 3 endpoints or 4 endpoints or however many nodes. Understanding that kube proxy actually takes that traffic and just sends it to the right place inside the cluster based on that internal cluster IP.
Got it.
But how is this different from Ingress? Because we're already getting questions about it. And we only have like 15 minutes left.
So very quickly, I think we want to talk about, so in the load balancer approach, there's also a way to run this as IP mode, which is just another way of exposing this application, but that allow it to get a dedicated IP address here on the VPC, which is a slightly more efficient network path for inbound connections. If you want to get more detail on the IP mode, you can read into this. But to answer the questions in chat on how this is different from Ingress, we have a separate module that goes into the Ingress approach. And so this is going to be a slightly different approach to the load balancing using the application load balancers. And as Justin mentioned earlier, this is going to give you slightly more control over, layer 7 routing and header checks and a few other features that you might want to use. For example, you might want to route one application to the dogs endpoint of your application and another application into the /cats endpoint. That's a simple way to kind of route multiple pods on the same domain and use Kubernetes routing mechanisms to help you do that. And so Ingress is pretty smart at being able to let you do that and translate those. And then the add-on will help you translate those to the actual.
Right. Path-based routing is very common, and it doesn't always mean that it's the same server or the same pod. It just means that, hey, these different paths in the URL need to go to different places. And Ingress and anything layer 7 is what would handle that. And Ingress is only for layer 7. You can't do IP sockets with Ingress. But the AWS Load Balancer Controller also can handle Ingress rules and create application load balancers instead of NLBs for you. So you can have different models for running Ingress. Application load balancer, you can say, or the load balancer controller, you can say, give me an ALB for every Ingress rule. You can share some of those rules. A common practice, at least historically with Kubernetes, was to run Nginx inside your cluster as a reverse proxy. And so you had an NLB coming into Nginx, and Nginx would then figure out all of those rules. And Nginx would be your load balancer or your Ingress controller internally. In this case, the load balancer controller, we can use ALBs directly. We could also run something internally, but running those ALBs gives you all the flexibility of an ALB and the scale of running ALB external from the cluster, where you don't have to manage it. You don't have to manage that lifecycle in the cluster itself. It's just another thing that you can say, I just want to use what what AWS provides, and then let me route the rules how I want to based on HTTP requests with headers and paths and all that other stuff.
You got it. And actually, we have an example in the multiple ingress pattern that goes into exactly that. And if you go through this, and we won't do it right now, I think we've got about probably 10 minutes here, and I want to get to the stateful sets, but I do want to show that in this module, we cover how you can route the /path, just the homepage, to the main UI service. and you could have a different application. So the catalog app routed to the /catalog endpoint. And so this is a very simple example about how you can use ingress rules to host both of those applications. And you'll see here that when you do that, the catalog ends up running on one address. They're both running on the same endpoint, but they're going to be served at different paths. So UI at the base path, and then catalog at the /catalog path. I think this really does cover just the basics of the load balancer controller, but I'd say probably 90% of use cases for most of our customers out there. We do have kind of more advanced networking modules if you get into the networking, where we talk specifically about things like security groups for pods and setting up, probably more relevantly, custom networking. I know that a common complaint or kind of problem that our customers run into is IP exhaustion, and custom networking can help you get access to more IPs in your cluster, and a couple of other common use cases that we cover in the networking module. But really, this module is all about the fundamentals, the basics, and we geared this in a way that you can be completely new to Amazon EKS and still get through this module. Lastly, well, before we jump to the last piece here, Justin, anything else that you wanted to add specifically on the exposing applications piece? I see we've got a flurry of questions in chat.
Yeah, I'm trying to keep up with some of the questions, because this is a really difficult part of Kubernetes. And I would love to see people run through the workshop and give feedback on things that still weren't clear. If there was something in here that you ran through and you said, I still didn't understand why this happened or what was working or not working here, please open an issue, please open a PR, because we want to make that workshop as clear as possible for anyone starting here. Because that side of things, where once you hit traffic and someone says my load balancer is not working or I can't get to my application, that often gets confusing of what layer you should start troubleshooting. And so we want to make sure that we have as much clarity in the workshop directly, that everything works by default, but also we can help you understand with more resources, and whether that's something directly in the workshop or another website, Kubernetes documentation, more videos that we need to host. There's a lot of options there that we can provide to make sure that this is as clear as possible. So please open those issues and PRs, because that's where we want to get started.
Absolutely. All right. So I want to talk about the storage module, but we're coming kind of close on time. Now, broadly, I do want to give a high level overview, and Justin, keep me honest here. So storage is a critical concern when you're working with containers in Kubernetes, because at the end of the day, if a container disappears and you're using the local storage, like the file system, it's gone. And so you want to be careful when you're running stateful workloads in a Kubernetes environment, that you have some sort of state. And so this can come in a number of ways. You can attach drives to the nodes that are powering your Kubernetes cluster. You could take advantage of database services out there, something like Aurora for like a MySQL database service, or RDS. But critically, when working with Kubernetes, we find that the use of persistent volumes and persistent volume claims makes managing stateful workloads in Kubernetes that much easier. And critically, here we have 2 tutorials for working with EBS and EFS, and FSX is on the way. We do have a contributor working on an FSX module right now. But in this particular module, we go through working with stateful sets with for EBS and EFS. Anything specific you want to add there, Justin?
A big thing with stateful sets is data is hard to manage, and it often requires some sort of consistency in how it's managed. So when a stateful set is provisioned, in this case a MySQL database, MySQL replicas not only assume that they have some storage they can rely on, but if I have multiple of them, they need to be named consistently. And that was something to me that, as stateful sets were being created in Kubernetes, was weird, because we kept saying that, oh, all pods should be disposable and they get random names and they're part of the deployment, all this stuff. But with stateful sets, we want them named 1, 2, 3 in a consistent manner. And when we need to deprovision them or scale down, we scale down 3, 2, 1. Like, we can't just say, oh, just pick one and get rid of it, because a stateful workload might depend on some of that naming, how the data was provisioned, how it was divvied up between the other containers. So all of those things are really hard to do. With things like EBS and EFS, it makes that a lot easier because you're not relying on direct attached storage to the node and then always provisioning the workload back to the same node and saying, I need you to mount this folder. You can actually say, EBS is a service that exists. I can attach an EBS volume externally, and it gets provisioned as block storage underneath the container at provisioning time. There's plenty of other storage services. You don't have to store things this way. Please use RDS if you're able to. Please use a hosted database service if that is an option for you. It'll be much easier. It'll be simpler just to say, hey, here's an external thing that runs this thing. But we also understand that stateful workloads inside of Kubernetes are very important for a lot of reasons. And so stateful sets were created. They exist inside the cluster. This gives you a couple different options of using EBS or EFS, and like you said, XFS, to get some sort of storage, whether it's block or file or something else underneath the container that can be mounted consistently without hard coding it to a specific node or a specific, IP address or something like that.
Yeah, and we tend to see this a lot with customers that are migrating maybe legacy workloads to Kubernetes and container-based deployments, because a lot of times they don't have the flexibility to immediately refactor their applications to be stateless, to use cloud services for storage, that kind of thing. And so in this case, we have a catalog service that utilizes the MySQL database that we're going to have running within the EKS cluster. And so we have a stateful set here. Again, I don't want to go too much into the weeds here, but let's just go ahead and describe that particular stateful set for the MySQL. We can see that it exists. There's only one replica running right now, but really what we want is for it to look something like this, where we have each pod, and like Justin said, they're labeled 1, 2, and 3. They're made from the same spec, but they're not interchangeable. These pods are not interchangeable, and that's like the critical thing with stateful sets. And so throughout this, what we do is essentially we create a test TXT file, and then we make sure that it actually exists, and then we delete the pod. Oops. And we wait for the pod to come back up. Enter a little too quickly there. Should be fine. And then as soon as the pod comes back up, we're going to run that command again, and we'll see that that text file is now gone. There's no such file directory. So essentially, we're not persisting state right now. As soon as we delete that pod, it's gone. Local file system doesn't exist anymore. And so what we want to do is we want to mount a drive on that particular endpoint so that when the pod disappears, the drive still exists, the data still exists. And so to do that, we'll use the EBS CSI driver. Justin, do you want to quickly talk about what the CSI driver is doing for the users here? Oh, I think you're on mute, but...
I did it again. I was trying to unmute myself as I was typing because I have a mechanical keyboard, whatever. CSI driver is an interface for containers to get storage. It's just a consistent way that any storage behind the scenes will be provisioned the same way so that the container runtime can say, I need storage, whether it's block or file or something else, and it's pluggable on the back end. So if you're on-prem, you can use NFS and you get file storage. If you're on physical servers and you need a hard drive mounted, you can have these plugins that let you pull that in. The EBS CSI driver will provision EBS volumes and make sure they're mounted for your workloads as needed. When the volume or when the application says I'm starting up, I need this volume, the EBS driver will provision an EBS volume if you need it, or remount that if it already exists. And so that driver is all about making sure that EBS inside your applications works seamlessly. And you can just say, when your application says I need storage, it gets storage. There's also things like storage classes and all these other advanced things for like, I need high speed storage, or I don't care storage, whatever the case may be. EBS has a lot of options, and the EBS driver allows you to marry those options to your workloads inside of Kubernetes, because Kubernetes is generic and it doesn't know about every option available on every storage platform. The drivers that plug in that storage to the workload is where it's responsible for saying what's possible or how I mount it into the workload.
Right. And I think I missed a step here. I was running into an error, but regardless, what we end up doing in this workload is essentially creating, we're updating the database endpoint that the application actually uses to use that MySQL that's hosted on EBS. We show how, by using that EBS CSI driver that Justin talked about, we're able to automatically provision a volume by creating what's called a persistent volume claim. So our pods will actually ask for that persistent volume. And then, this goes through, accessing the PV, seeing the actual PV in the AWS console, the persistent volume, or the EBS volume. And then we run that same test again to see that we can actually access the test.txt file after deleting the pod. And we'll see that we can. Now, I wish I had more time today to actually go through the full workshop here, but the benefit is, folks, you can go ahead and start doing this yourself at home today. Go to EKSWorkshop.com. In the first module, we have a setup phase where you can actually provision the entire workshop cluster environment with a single Terraform command. Now, of course, there's going to be a few requirements. You got to have enough VPCs available in your account. But the great thing is the Terraform will actually walk you through whatever issues you might be running into. And so you can kind of help, you can kind of work through it, debug anything that you might potentially run into. If you have any issues, by the way, feel free to open an issue on the repo. We are actively monitoring right now. We just launched today. So we've tested on our machines and, to the best of our ability. But we can't cover every use case and every user machine. So if you do run into an issue, please let us know and we'll get it rectified as soon as we can. By running this one Terraform command, you get the cluster environment and you can start working through it at your own pace. By the way, if you're a customer watching this and you want to have an AWS hosted version of this event where we'll host it on our infrastructure, you can reach out to your account rep. We're pushing this out internally so our field team, our solutions architects are able to execute this workshop as well. Justin, anything you want to say before we close out here?
Thank you, everyone, for asking questions and joining, because you made all the content better, just to add more clarity. So we already got one issue open, which is awesome to see. Keep them coming. We want to keep improving this over time. We're going to keep it updated with new versions of Kubernetes and EKS that come out, new features that come out in the controllers and Terraform blueprints. So this is starting today. We want you to get started, give it a try, but this isn't the end of the workshop. We've been managing a workshop for years now, and people love it. We love that so many people have been learning from it, and we want to keep improving it over time. So please keep those PRs and issues coming so we can help improve it for the next generation of people that are trying to learn.
Absolutely. And be sure to subscribe to Containers from the Couch on YouTube. We're going to do more of these episodes. We've got module chairs that led each of the different modules here for networking, security, automation, all of them. We're going to do more of these live stream episodes. Be sure to subscribe again to Containers from the Couch. Thank you so much for joining us, for all the great questions in chat, and we'll catch you next time.